Okay, and here will be some more example for you to try. Okay, I would like you to solve y double prime. Sometimes it might be in this form. Okay, second derivative of y with respect to x minus dy by dx minus 30y. Okay, it's equal to 0. So in this case, you can write down in this form y double prime minus y prime minus 30y is equal to 0. So you can find characteristic. You see, in this case, you don't need to use r. You can use any variable. Okay, let's say I use m. So get m squared minus m minus 30 equal to 0. And you can see this one is very easy to factor. So we have m minus 6 times m plus 5 is equal to 0. So you get m equal to 6 and negative 5. When you see this, of course, this is the first case for distinct real roots. So you get y1 equal to e to the r, t, right? But right now, you see x, we don't have t anymore. X is independent variable, so y1 e to the 6x, and y2 equal to e to the negative 5x. Therefore, the general solution will be y equal to c1y1 plus c2y2. And you just plug it in. So it's equal to c1y1 e to the 6x plus c2y2 e to the negative 5x. Okay, just like this. Okay, one more example on this page. Now I give you second derivative of y with respect to x minus 6 dy by dx plus 9y is equal to 0. Okay, you see that? So we have what? Y double prime minus 6y plus 9 is equal to 0. Characteristic equation, you get 1m squared minus 6m. Oops, sorry, I'm missing the prime. We should have the prime here. Plus 9 is equal to 0. And you can factor this one gonna be m minus 3 times m minus 3. So it's m minus 3 squared equal to 0. So you have m equal to 3 and 3. Repeated real numbers. Therefore, y1 equal to e to the mx, e to the 3x. And instead of having exactly the same solution, e to the 3x, you need to multiply independent variable into here, right? So y2 is x e to the 3x. And don't forget, when you write out the general solution, you have y equal to c1y1 plus c2y2, which gonna be c1 e to the 3x plus c2x e to the 3x. If you use this method, okay, you can make sure that your two solutions, y1 and y2, they are linearly independent. Okay, and I have this one. Okay, before we see more example, let's come back here a little bit. Okay, here we go. Okay, this one is for higher order. Still, it's gonna be homogeneous, linear, ordinary differential equation with constant coefficient. But now the order, okay, we are not going to do the second order anymore. It can be anything higher. So that's why we say higher order. Let's see the first example. We want to solve y triple prime minus 3y double prime minus y prime plus 3y is equal to 0. The question is, can we still find the characteristic equation? The answer will be yes, of course. So for here, the characteristic equation is this one like third derivative. So you're going to have r cubed minus 3 second derivative r squared minus 1 first derivative, so you have 1r and plus 3 because we don't have any derivative here. This is the technique, okay? When you see this, you kindly you have to think ahead a little bit. So I mentioned about grouping. So from here, see, if you group these two terms together and these two terms together, then when you factor r squared, the common factor r squared from the first group, you're going to get r squared times r minus 3 and minus, okay, you factor minus out. So inside parentheses, you're going to have r minus 3. And then these two terms, you have common factor r minus 3, you factor r minus 3 out. You have r squared from the first term and just minus 1 from the second term. So you get r minus 3 times r squared minus 1. This one, what? It's the difference of the square. R squared minus 1 squared. You can break it down to be r minus 1 times r plus 1. Therefore, now you have three roots. R1 equal to 3, R2 equal to 1, and R3 equal to minus 1. How you find it? You just need to set each factor here equal to 0. Okay, this is how you find the roots. You set r minus 3 equal to 0, so you get r equal to 3. You set r minus 1 equal to 0, you get r2 equal to 1. And you set r plus 1 equal to 0, so you get r equal to minus 1. And you can see these three values are all different. Therefore, we have distinct real roots. So the first solution, y1 equal to e to the r1t, which is e to the 3t. y2 equal to e to the r2t, e to the t. And y3 e to the r3t, negative 1t. And don't forget, once you know y1, y2, and y3, you need to write it in terms of general solution. So y equal to c1y1 plus c2y2 plus c3y3, which is equal to c1 e to the 3t plus c2 e to the t plus c3 e to the negative t. See, it's not that bad, right? So this case is for the third derivative. Okay, let's see next example. How about this one? This one you have fourth derivative. You have y to the fourth minus y equal to 0. And y is a function of t. Similarly, you still be able to find characteristic equation. So this is what? You see the fourth derivative, you should have r power 4. Minus this one, you don't have any derivative with it, so it's just constant. So minus 1, you set it equal to 0. Then you can factor this out. So it's what? The difference of the square. So you have r squared minus 1 squared. So you get r squared minus 1 times r squared plus 1 is equal to 0. And you can break the first term down into r minus 1 and r plus 1. And for this one, it's actually what? It's r squared minus, right? Minus I squared. Because I equal to negative, is negative what? I is square root of negative 1, right? So we can break this down to be r minus I and r plus I. You set it equal to 0. Here we go. Right now we have r1 equal to 1, r2 equal to minus 1, r3 is I, and r4 is negative I. As I mentioned before, how we find r1 to r4, you only need to set each factor here equal to 0, and then you get all the 4 values come out. But right now it's a combination, okay? This one, r equal to plus and minus 1, is what? Distinct real numbers. How about this one, plus and minus I? This one is complex number with alpha real part equal to 0 plus and minus 1 I. So beta equal to 1, imaginary part. Therefore, okay, now we're gonna write in the combination of all things here. So y equal to c1y1 plus c2y2 plus c3y3 plus c4y4. But don't forget, distinct real roots, you have c1 e to the r1t, so e to the 1t, plus c2 e to the negative t, plus e to the alpha t, but alpha equal to 0, so it's 1, times c3 cosine beta t, plus c4 sine beta t, but beta equal to 1, so this is what we get. Now we can expand it into this form. This is how we write the solution. You see, in one problem, it doesn't matter that you have all the roots gonna be all distinct real numbers, repeated roots, or even though it's a combination between distinct real roots and complex number, just like this example, you always be able to work on it, just use exactly the same idea of how to write the solution. Okay, I have a few more example for you. Okay, let's see this. Here we go. All right. Okay, let's come back to this example. I think it's a good example. So this one, I give you try to find the solution of what's that? Y double prime minus 4y prime plus 13y is equal to 0. I actually borrowed this example from my colleague. So thanks, Dr. Palop, right here. So we this one I just want you to see, instead of having t as an independent variable, you can have x. So this one we have what? Y double prime minus 4y prime plus 13y equal to 0. And we can write characteristic equation to be m squared minus 4m plus 13 is equal to 0. And once again, you can see here, similarly to what we did before. So you can see a equal to 1, b equal to negative 4, and c is 13. Therefore, you have a quadratic formula. The two roots m12 is equal to minus b plus and minus square root b squared minus 4ac, all divided by 2a. Keep plug in the value. B equal to minus 4, so minus 4, you get 4 plus and minus square root b squared minus 4ac, all divided by 2a. Okay, this is what we get. And you can see 16 minus 52, it's negative 36. It's actually what? 6i. So you simplify, you get 2 plus and minus 3i. So now a equal to 2 and b equal to 3. It's just like your real part alpha and beta here. So you have solution y equal to e to the ax or alpha x. Okay, you plug 2 in here and times c1 cosine imaginary part bx plus c2 sine bx. So now you have a equal to 2 and b equal to 3. Here we go. You plug in here. All right, and this a little bit more. Okay, so we have the third derivative, y triple prime minus y double prime minus 8y prime plus 12y equal to 0. So the characteristic gonna be m cubed minus m squared minus 8m plus 12. See, we don't have any m here anymore because we don't have any derivative here. And this one we can factor. So it's equal to m minus 2 squared times m plus 3 is equal to 0. If you don't know how to do it, let's go back and review some more about how you solve polynomial function. okay? If your polynomial function up to degree 3, that means you're gonna have at most 3 solutions. So this one, even though we have repeated root 2, 2, and this one minus 3, but we can count here as a 2 solution. So we're gonna have at most 3 solutions. It doesn't matter if they are gonna be distinct or not. And yeah, okay, so please review, like how you get this. Can you do it by yourself? If you have 12, you need to find the factor of 12, which is what? 1, 2, 3, 4, 6, 12, right? And then you have to do the matching, guessing, like which one can make the whole equation here equal to 0. And I found that 2 and minus 3 can make it become 0. All right, so we have repeated root. The first one, y1, gonna be e to the m1x. But then m1 and m2, they are exactly the same thing. So for repeated root, you have to multiply independent variable term here. So you have x times e to the 2x. And this one just the distinct one, so e to the negative 3x. And when you write the general solution, you're gonna have y equal to c1y1 plus c2y2 plus c3y3. Okay, just plug in each term here into this notation and you get the solution. All right, and this should be the last example. Okay, let's do it. So you have, what's that? The fourth derivative of y with respect to x plus 4 times the third derivative of y with respect to x plus 4, the second derivative of y with respect to x minus 4 dy by dx minus 5y equal to 0. What's the characteristic equation? So it's what? M to the fourth plus 4m cubed plus 4m squared minus 4m minus 5 is equal to 0. And this again, we can use like factoring, okay? So we get m plus 1, m minus 1, and this term. But this term we cannot factor it anymore. So we have to use what? Quadratic formula again. Okay, so the first two factors here, you set them equal to 0, and then you get m equal to negative 1, and this group give you m equal to 1. Since we have polynomial degree 4, so we're gonna have at most 4 solutions. So find 2 more here. We're gonna have a equal to 1, b is 4, c is 5. So you plug into quadratic formula, minus b plus and minus square root b squared minus 4ac, all divided by 2a, okay? You simplify this one, 16 minus 20, so you get minus 4. Minus 4 is what? 2i, and you divide through this by 2, you get negative 2 plus and minus I. So real part will be minus 2, and imaginary part is what? 1. Okay, so what's gonna be the general solution? Y equals to c1 e to the m1, so minus x, plus c2 e to the m2 x, 1x, plus e to the real part, negative 2x times c3 cosine b x, which is 1x, plus c4 sine 1x, and now c1, c2, c3, c4, right now just constant. And if the problem don't give you any kinds of initial conditions, so you just leave the constant term right here. And let's see what else do I have for you. Oh, okay, this one. Here we go. All right, and I would like to give you a few more problem for you to try on by yourself. Okay, let's see. The first one was that the 2y double prime minus 11y prime plus 12y equal to 0. So this is gonna be the solution. It's y equal to c1 e to the 3 half x plus c2 e to the 4x. So when you see this solution, you can guess that this one should be the first case when you have distinct real solutions or distinct real roots. And this one y double prime plus 10y prime plus 25y. See, you see one more x here, and the exponential term are exactly the same thing. So this one should be the repeated root. Number 3, you have y double prime minus 2 y prime plus 5y. You see sine and cosine, this one should be complex number. And your root should be what? 1x, so it's 1 plus and minus 2i. Okay, and this one, 3y double prime minus square root y prime equal to 0. Okay, just find that and you should get two distinct real roots. And what's that? This one y double prime plus 16y, of course, is gonna give you complex roots, and real part should be 0 and imaginary part gonna be 4. So you have plus and minus 4i for this one. Okay, please give a try on that. And okay, we will continue. If you have any question, feel free to ask me through any application that we use.